In this practice, we'd like to find the magnetic field in the coils. But first of all, we'd like to review the Ampere's laws. Ampere's law said, if you consider some closed path, so this is a small length vector is dl, and the magnetic field is directed some directions, and we'd like to integrate over the magnetic field over a closed path. So this is integral of the B dot dl. So this is scalar product. And this circle means closed path. Then this is equal to the current passing through these regions. And if you use this is a positive direction, this is the positive direction, you can use a right hand rule. So following the DL is following the fingers, 4 fingers directed toward the direction of the DL. Then some point to the direction of the positive direction. So this means this is a positive direction. Then sometimes we have a current is passing to this directions, I sub 1, and the current I sub 2 is directed same ways, but third current is flowing the opposite direction. Then in this case, right hand side becomes mu sub 0 times I sub enclosed. This becomes, in this case, this is Ampere's laws. In these situations, becomes I sub 1 plus I sub 2, because this is same direction with the positive directions, minus I sub 3, because I sub 3 is directed the opposite directions. So this is Ampere's law. We can apply the Ampere's law to discover the magnetic field inside of a coils. So we consider very, very long coils. And the axis of the coil is equals the G axis. Then we'd like to find out the magnetic field inside and outside of the coil. Then from the symmetries, we can easily discover Bx and B sub y have to be the 0 because of the symmetries. Because this is really, really long coils. So this is a little bit short coils, but this point actually corresponds to g to the infinity. This coil corresponds to g to the minus infinity. Very, very long coils we consider. Then from the symmetries, the symmetry, there is no special direction in the x, y directions. So we have to choose component, x component and y component of the magnetic field have to be the 0. So only that we have a z component. At first, we'd like to consider the path outside of the coil. This is the direction. So this is the integration path. Okay, then we'd like to find that this is rectangular L. For example, this is the axis to this point is R sub 1, and this point to the here R sub 2. Then we'd like to integrate. The magnetic field, actually only the G component. We consider this point is B sub 1. This point is B sub 2. And we'd like to apply the Ampere's laws. Ampere's laws said integrals over the closed path is equal to mu sub 0 times I enclosed. So this case is that there is no current passing through this area. So I is 0. So this means right hand is 0. And the left hand side is directions of the integral path is exactly same with B sub 1. So in this case, you can usually B sub 1 L. And but B sub 2 is the opposite direction. So minus B sub 2 L. So from this equation, you can cancel the L. Then we have a really important equation. B sub 1 equal B sub 2. So if we have a magnetic field outside of the coils, magnetic field have to be the constant values. So outside of the magnetic field is always constant. Then we could consider the really far away. I'll go to infinities. Then actually at this point, we don't know much about the existence of the coil. So at the infinities, B have to be the 0. So actually this is going to be equal to the B equals 0. So we have to connect these two. So at the infinities, magnetic field 0. So this means outside of the coils, magnetic field 0. Coil, magnetic field is 0. This is the result of the first result. Then we'd like to discover the magnetic field inside of the coils. Then again, we'd like to draw the coils. This is the z-axis. And then to derive the coils, we'd like to write down the current. This is the current, direction of the current. In this region's current is flowing through the board, but this side is current direct toward us. So if you look at this weights, so just only the single current coils, then this directions of the current is this directions, and this ones, and come to this one. Okay, this is the directions of the current, and we just only find the cross section. Then we'd like to apply the Ampere's laws. But first of all, we'd like to consider this path of the integrals. So we'd like to consider this path of the integrals. Okay, so this is integration path. As I explained, outside the coil, B is 0. And then from the symmetries, actually we have only the G component, BG, even inside of the coil. Then we'd like to apply the integration Ampere's laws. Ampere's law said integral of the B over the closed path is equal to mu sub 0 I enclosed. And the left hand side it becomes, if you consider this length is L, this becomes B G L. This is the left hand side. Then the right hand side, mu sub 0. The directions of the areas, you can use the right hand rule to find out the directions is this ones. You can use the right hand rule. To find it. And this direction exactly same with the direction of the current. Then you should count the number of the current passing through these areas. This area. Then you need to find out how many turns of the coils per unit length. So this is a coil has n turns per unit length. Then you have to multiply the length of the L to find out the turns of the coils. So this means N L. How many turns of the coil? Number of turns. Actually the current is I. Then if you look at the both sides, actually the L appears in the both sides. So we could find that B sub G is a mu sub 0 N I. This is a magnetic field inside of the coils. So finally, I'd like to conclude. Outside of the coil, B is 0. Inside of the coil, B x B sub y is 0. But B sub G is expressed mu sub 0 and I is a current. Okay, this is the end of this practice.